All right, with chapter 4.3, we're going to be doing some exponential modeling. So we're going to be looking at contexts and situations where we have either perfectly exponential or almost exponential functions that will be used to model those situations. Okay, I went ahead and wrote the general formula for an exponential function. Here, that's our n of t is equal to p times a raised to the t power. That a raised to the t power is what makes this an exponential function. T being the exponent is telling us how many times we multiply a together. So if, for instance, I have a to the third, that would be 3 factors of a times a times a, just for a little background information there. Okay. Your job when you're trying to come up with these exponential functions, when you're trying to really model these situations, is to determine the value of p and to determine the value of a, which is that common ratio. Okay, p is the initial value. It's the function value when t is equal to 0. In some of our examples from class, we've been talking about different experiments, and this would be right when that experiment starts. What is the function value? Okay, a, the common ratio, is what determines if we have a growth or a decay function, exponential function. When a is greater than 1, something, for example, like 1.08, if that's my a value, I have a growth function. Okay, I have a growth exponential. If I have a between 0 and 1, something like 0.42, well then I'm in a decay situation, and the corresponding function is it is decreasing. So let's look at, just to be thorough here, I want to get some visuals going. So at the top of the screen, I'm going to just reiterate what these graphs look like in a very basic drawing. All right, so let's look at what happens when we're using a growth function. Well, that would mean that our a value is greater than 1. So what happens is we start off with our initial function value, and the growth rate causes our function values to grow faster and faster and faster, and it would look something like that. If we were in a decay scenario where our a value is between 0 and 1, we would have some sort of starting p-value, and we would be reducing or decaying away those function values. They would get smaller and smaller and decreasing. So that's just a little summary of what you need to be keeping in mind as we move through the next few homework problems. Of course, if you have any questions, you can send me an email, or you can come to my office hours on Mondays. Feel free to reach out again if you have any questions. As with all homework problems, you need to read the question and understand the context before you get started. You should have a plan and try the problem before you listen to the solution. So take a second now, read through the question, and try out your plan. Come back if you still need to see the solution. With all of these problems, when we're trying to come up with a formula, and it tells us straight away in the question that we are trying to find the formula n of t, you need to just go ahead and write out what the formula is that we're trying to determine. We know it's an exponential function, so the form is p times a raised to the t power. This should appear on every problem that we work today, in some form. The problem gives us a list of pairs of data. It tells us when t is 4, n equals 9. When t is 7, n equals 49. And our goal here is to somehow use that information and an exponential function n to determine when t is 13, what is the value of n. So using the definition of these t in pairs, I went ahead and just substituted those values into the formula, the generic formula. So n is on the left-hand side, p times a raised to the t power is on the right-hand side. I've just plugged in where in this first pair I see an n, I wrote 9 instead. Where I see t, I put a 4 instead. I did the same thing with our second pair of data here. Our second data point here, I've got when t is 7, n is 49. In our previous work, we have solved systems of equations using different methods. And I'm going to kind of call on that information now in order to help us solve for the values of p and the value of a, so that we can fill in p and a in our n of t formula. I want to let my calculator do as much of the work as possible, but in order to make that a possibility, I need to solve these equations for one of the variables that are here. I have a p, I have an a. I'm going to solve both of these equations, solve both equations for p. When I do that, I'm going to use the crossing graph method in order to solve for a. All right, so that's our goal. That's what we want to do, or I'm sorry, that's our solution path. Let's see if it'll work. So in my first equation here, I have 9 equals p times a raised to the 4th power. A raised to the 4th power is just some number. It's a multiplied by a multiplied by a and multiplied by a for a 4th time, but it's still just some number. So what I can do is divide both sides of the equation by a raised to the 4th power. I don't know what that number is right now, but it's just a number. It's a constant number. I've got a to the 4th in the bottom and a to the 4th in the top here, so I'm able to reduce those. I'm left with p equals 9 over a to the 4th power. And that's my first equation solved for p. My second equation, I'm going to work that on this side here. I have 49 equals p times a to the 7th. Well, it's the same scenario. A to the 7th is just a multiplied by itself 7 times. So it's just a number. I can divide both sides by a to the 7th, and you can see what happens on the right-hand side. It reduces down, it leaves me with just p. And I'm left with 49 divided by a raised to the 7th power. So now I have two equations that have both been solved for p. To use the crossing graphs method, what we need to do is type y1 equals, let's separate this out here now that we're moving into the crossing graphs method. Okay, we learned this in 2.4 if you need to go review this method. We're going to type in 9 divided by a raised to the 4th power. Our y2 in our calculator will be 49 divided by a raised to the 7th power. And in this way, in our calculator, I just want to fix one thing here. In our calculator, it only knows really y's and x's when it comes to graphing. And so instead of typing an a, I want to type an x. So y1 equals 9 divided by x to the 4th. That's coming from the work we did here, solving for p. We're treating y like p and a like x. Then I've got my y2 is 49 divided by x to the 7th. And again, that's coming from the work we did here. You can go through using your calculator, second, trace, that's your calculation menu, and select option 5. That's going to calculate the intersection of these two graphs. So go ahead and type these into your calculator and find that intersection point. See if you get what I get. I'll give you a little hint here if you're having any struggles. You can change your window to only include the first quadrant of the graph, which means x min is 0, x max is 10, y min is 0, and y max is 10. That's where we want to look to find this intersection point. That might help you narrow it down. When I solved this out, I saw a graph that looked something like this. And this is just a sort of general sketch here. What showed up for me between 0 and 10 on the x and 0 and 10 on the y was some sort of decreasing function here. Let me get another color going here for the other function. And there's that. somewhere in here, there was an intersection point. So I followed the prompts on the calculator to find that intersection point, and what it returned was an XY pair of, and I'm going to write down more decimal points than you probably ever would, and I want you to do the same. 1.7921. Okay, that's what I got from my X coordinate. For my Y coordinate, I got 0.9396607, but I'm going to leave, got to truncate somewhere here. This is my XY. What I want you to remember is that we weren't really using X and Y when we started this problem. We were using A, which got represented by X in the calculator, and P, which got represented using Y in the calculator. So by using these two functions and the crossing graph method, we were able to determine that in our formula, n of t, the P value is our Y value, so it's something approximately like this, 0.93966, sort of rounded down there. That t is always there, that's our exponent, and the A value was approximately 1.75921. So you have a couple of options in order to meet our final goal, which is finding n of 13. So if you go back and you read the question, why have we been doing all of this? Well, first we needed to find a formula for n so that we could calculate our final goal, which is n of 13. What is the value of n when t is 13? We're going to round to the nearest whole number. Now that we have a formula, it's going to be pretty simple for us to figure this out. We've got, it looks like I'm going to run out of room, so I'm just going to kind of go on to the next line here. 0.93966 times 1.75921, all raised to the 13th power. So what you can do is either just plug this in to your regular home screen and let the calculator do that calculation for you, a little multiplication sign there if you're going to put it in the calculator, or you can enter in y1 is equal to 0.93966. These are all just approximations. 1.75921, all raised to the t power there. And then you can use the table functionality of the calculator to go get this value. No matter how you do it, what we're going to do at the end is round to the nearest whole number. All right, so go calculate that and come back and check and see if you got what I got. All right, so I typed this into my calculator, and n of 13 turned out to be, let me bring this down here, n of 13 for me turned out to be approximately 1452, so 1052.4. And I'm only writing that first decimal place because we're rounding to the nearest whole number. If I was going to round this, I would need to round it down, not because we have some context with like live bacteria or anything like that where you need to pay attention to what's alive and what's dead, but because this 4 in the 10th place tells us the nearest whole number is actually going to be rounded down to 1452. So this is what I'm getting using my numbers from the problem. All right, so up here, n of 13 is 1452. Notice how we had to find the formula first in order to determine what n of 13 was going to be. Question number 5 is quite different from the last one. We're trying to test the data to see if they're exponential or not. What we need to do is try to see if there's a common ratio, that A value, between the different Y values. All right, so I'm going to show you how to do that now. I went ahead and labeled the different Y values in order. I've got Y1 and Y2, Y3, and Y4, and I'm only referring to the 5, 10, 20, 40 in the bottom row. Those are my Y values that I've labeled here. What we're going to do now is check for that common ratio. The way we do that is we take a y value and divide it by the previous y value. And we have to do this for all of the y values here. So I'm taking y2, dividing it by y1. I'm taking y3 and I'm dividing it by, y2. y2. And I'm going to take y4 and divide that by y3. I don't know why I keep writing a 4 for that y. I apologize. I'll fix that here. If the ratio of these pairs of y values is constant, if it's the same all the way through each of these ratios, then we do in fact have exponential data in our table. All right, so let's go ahead and substitute in these values. y2 is 10, y1 is 5. Put this in your calculator, or maybe you just know 10 divided by 5 is 2. Let's do the next one. y3 is 20, y2 is 10. We can divide that out and we're going to get a value of 2. So right now it looks like these two match up and we have a common ratio, but you have to test every single pair in the table. So then y4 here, let's look at this, is a value of 40. y3 has a value of 20. 40 divided by 20 is 2, and look at that. There is a common ratio between all of the y values. Okay. Therefore, this is an exponential data set. So once you find that there is a common ratio, a lot of you are going to be tempted to think that that is your A value. That is not your A value. Just because there is a ratio between the terms, right? That's what tells us this is exponential. It is not what tells us the A value. Okay, so I'm going to just kind of clean up my workspace here, and I'll show you how you can find that actual function. So in the second part, we're looking for this actual function here. Well, what you need to do is remember that when you have a table, this is data, okay? A table is data. And anytime you want to do work with the data, you're really doing some statistical work here, all right? That's our science of data. So what I need you to do is hit your stat button on your calculator. You're going to do stat and select the option for edit, because what that's going to do is it's going to let you edit a couple of lists, and actually it orients vertically. Okay, so you're going to have your L1. I want that to be all of your X values, 5, 10, 15, 20. They're regularly spaced here. Then I need your L2 values to be your Y values. Okay, these are your function values, 5, 10, 20, and 40. This is what your L1 and L2 should be in your calculator. Once you've inputted all of the data that you have for your table, don't leave any pieces out. It affects the model that comes out, okay? So don't leave any pieces out. What you need to do is hit Stat, select the Stat button. This time you need to go over to the right. So we're not in the Edit menu. We need to be in the Calculation menu. And you need to scroll down. So scroll until you see EXP REG. That's exponential regression. You give it data and it tells you the exponential function of best fit. That best passes through all 4 of the given points. All right, so go ahead and do this procedure and see if you get the one of the functions that's in this set here. We know it's exponential, so this final piece is out. But does your calculator give you a function that is one of the selections that are left? My calculator returned a function, and it kind of gives it to you in a weird way. Okay, it tells you the form of the function at the top of the screen. Y equals A times B to the X. You are used to seeing your A value where the B is. So you need to pay very close attention to where these numbers actually go. Remember, the calculator, it has a predetermined usage of letters like X and Y and A and B. And we have other ways that we learn it, like whenever we were doing linear regression and you have a y equals mx plus b, that didn't always match up with what the calculator had predetermined those letters to be. So just pay very close attention when you're substituting in here. I have y equals, oops, let me just show you exactly what the calculator returned actually. I got an a value of 2.5, and this is the calculator's a value. It's not the a value that indicates a growth factor. Then I got a b value in my calculator of 1.148. 1.148. Okay, so that is my growth factor in this case. So what we need to do is substitute the a in and the b in into this formula. So y equals 2.5 times 1.15, I'm rounding up just to match the number of decimal places in my answers, okay, raised to the x power. And so you can kind of see right here, I'm doing 1.15 from that 1.148. This is the exponential function that best fits the data from the problem. And you can see that, at least with mine, the numbers that I was given, it's this fourth selection here. 2.5 times 1.15 raised to the x power. This problem is very similar to the first one that we worked together in that you're given some sort of data pairs when t is 1, n equals 8, and you're given some information that when t equals 3, n equals 32. In the first problem, they would say something like, well, tell me what the value is when t equals 13, okay, just to call back to that first problem. But instead, this time, they just want us to stop after we can determine what the actual formula is, which will have the form p times a raised to the t power. Now, if we just look at our data, when t gets bigger, it went from 1 to 3. N gets bigger, it went from 8 to 32. So I want to keep in mind that I have a growth factor here, okay? I'm getting bigger, I'm increasing over time. This is not a decay situation. So my a value better be greater than 1. That's just a way to check your work and make sure that you're on the right track as we go through this problem. Since I already showed you kind of the long way to work these problems out when I worked out number 1, I want to show you the shortcut, and it's going to look a lot like the last problem that we did just before this one, where we end up using the statistical calculator in order to calculate what our function is going to be. So in your stat button, you have a few menus, and all you want to do is select stat and then edit. Right? In that stat edit, what it's saying is, all right, tell me all of the data that you have. Well, my t values go in L1, t equals 1, t equals 3. My y values go, or I'm sorry, my n values go into L2. That would be when t is 1, y is 8, and when t is 3, y is 32 here. Right? So I'm just putting, I only have 2 pairs of data. I don't have a lot of data to give this calculator, but that's enough. It's enough data to get a function of best fit. So what we can do now, once you have your data into the calculator, is you're going to hit Stat, Calculate, and I think it just says Calc at the top of the screen, so you're just kind of scrolling over to the right out of that Edit screen. So Stat, Calculate, and it's option 0. Option 0 is EXPREG, Exponential Regression. You're going to just press enter through all of the options in that menu, scroll down and hit calculate, and it should return something like this. Y equals a times b to the x, and it's going to tell you what the a value is and what the b value is in this function. When I put all of this information in using my numbers, the a value came out to be 4. The b value came out to be 2. So what we have to do now is just substitute in directly into the formula. I've got an a value of 4 times a b value of 2 and that 2 is being raised to the x power. Now, they did not give us information in y and x. We had to change the information into y and x in order to let the calculator do the work. So your job at the end of the problem is to go back to n and t. Our y value is an n value, y's are n's, x's are t's. So let's make those substitutions, let's make those changes. N of t, or just n, is equal to 4 times 2 raised to the t power. Once you have everything in terms of n and t, you can just type this into your function answer box at the top. 4 times 2 raised to the t power. I really like this problem. I want you to take a second and read it. This is number 10 in the homework. Make sure you understand what's going on here, because if you don't, doing the work is not going to be very helpful. Okay, you need to understand that a worker is looking at his wages over time. So as this worker reviews his wages, okay, he decides that he wants to see if the data is growing exponentially. And the way that you're going to do that is, as it states in part A, by calculating ratios. Okay? So we're going to look at the ratio of 15.35 divided by 15.2. Now the hint that it tells us is to round our answers to 2 decimal places. Okay, we're going to round to 2 decimal places here. Sorry, my phone was vibrating. So put that in your calculator and do that division problem. What I got out was about 1.0. .009 here, and it says to round to 2 decimal places. So we're going to look at the 3rd decimal place. If it's greater than 5, we rounded it the 2nd decimal place up, and that's exactly what we're going to do here. So my first ratio is about 1.01, okay? And I'm going to write that in yellow right next to the table, 1.01. That's what I got when I did W2 divided by W of 1. So now I'm going to look at the next pair of data and let's see if we get something similar. I'm doing W of 3 divided by W of 2, which is 15.50 divided by 15.35. That's approximately, pop that into my calculator. I only need to look at the first 3 decimal places, because I'm going to do some sort of rounding to 2 decimal places. So I'm going to check the 3rd decimal place. Since it's greater than 5, I'm going to be rounding up. And again, I wind up with a value of 1.01. I'm going to add that next to my table in yellow. The crucial part here, and a lot of people will stop here after doing it twice and they see that, oh my gosh, okay, the ratio is the same between all of this data. You have to do it for all of them. It's important that you hit all of the data points that you're given to make sure that all of the data follows the same pattern. Okay, so if you have a test or a quiz where you need to show work, you're going to need to do this for all of the different pieces of data. So now I'm doing W of 4, 1565, divided by W of 3, which is 15.50, 1550. Pop that into the calculator and see, do you get 1. I'm just going to look at the first 3 decimal places again. So when I divided 15.65 divided by 15.50, I got 1.009 again, which means that I need to round up my 2nd decimal place to 1.01. I'm going to add that back into my table 1.01. And you can see in part A, it's saying the ratios of successive terms are always constant Okay, I'm not sure what the drop-down box is going to say. It might say constant, it might say the same, it might say 1.01, something like that. But because those ratios are always constant, that means the data is exponential. That's the definition of having exponential data, is that it goes up by some constant multiple in every case. Now, some of you might be wondering, well, what was going on here? We had 1.009, and then we had a whole bunch of numbers after that, and those numbers weren't all the same, okay, for all of these ratios. The deal is that it's close enough to being a constant ratio between the terms that we can still use an exponential model, and it's going to work pretty well. Okay, so I've already worked quite a few problems that, we're just doing the same thing over and over again. So when you have this table of data, okay, and you're trying to do some sort of figuring out of a formula from data, you need to use your stat menu, okay? And you can reference those previous problems on how to use the stat menu to get your formula. So that's going to help you not only in part D, that's going to help you in part C and part B. So when I have data, I almost instantly pop that into the stat menu so I can see what the formula is going to be. Once you have the formula, your W of t function, okay, so I'm skipping from A all the way down to D here, getting my formula, and then using that to solve the rest of the problem. So your growth factor is going to be, here's the general form here, P times A to the T. Whatever the calculator spits out as your B value, that turns out to be what we've been calling the growth factor, or the A value, okay? And that's going to be what you get in part B of this problem. All right, so get your formula first, then go back. You can answer B pretty easily from there. And you can answer C by using your formula and plugging in 0. All right, it says in the question here, the worker cannot remember what he earned in 2000. So what we need to do is figure out how many years into this experiment is to the year 2000. Okay, if we go back up to the context, it tells us that this sort of measurement began in the year 2000. So in the year 2000, 0 years have passed. Okay, so we're going to let t equal 0 in our formula. The really good part about having your formula already ready to go is that not only could you just plug in 0, and that's going to tell you what your initial wage was, but if you have your formula, it's actually already there. The p-value in your formula is the initial function value. It is already in the formula, right? So my suggestion to you is when you're given data, use your stat menu and your exponential regression to determine what the model is. All right, once you have your model, you can answer the rest of these questions very quickly. All right, so I wanted to finish out this problem by giving you a little bit of information for parts E and part F. All right, we already saw how to do part D, which was by using that stat menu. All right, stat, you have to edit your L1 and your L2. Right, so that's in your edit menu. Then you need to do your calc menu, which option 0 is exponential regression. That's going to give you one of these 5 functions as your model. Okay, that models the wage growth. Now, in part E, it's asking us what percentage raise did the worker receive each year? We're going to use the model found in part D. All right. When I did the exponential regression on my calculator, I got a function that most resembles this selection, 15.05 times 1.01 raised to the t power. Now in 4.2, we started talking about percentages and about how we have this formula, and I'm going to try to use the right variables here. W of t equals 15, oops, let's be more general than this. The general form here is W of t equals P times A raised to the t power. Okay, so this A is our growth rate. It's our growth factor, okay? But what we need to think about is, as a percentage, how much is our function value going up each year? Okay, that wage, how much is it going up by as a percentage? So what we need to do is say A is equal to 1 plus R, okay, where R is the percent, but written as a decimal. All right, all of this is coming from 4.2 if you need to go review this information. In our case, let's look back at the function. We have an A value of 1.01, and that equals 1 plus R. So we need to do a little bit of solving here. Okay. I'm going to try to get R by itself, which means I need to subtract off this 1 from both sides, subtract 1 from both sides. And what you wind up with, 1 minus 1 is 0 plus R, so I just have R left on the right-hand side. And on the left-hand side, I have 1.01 minus 1. Well, that's 0.01. I need to turn that decimal into a percent. So to turn that into a percent, there's a couple different ways that I talked about, but I think the easiest way is just moving the decimal point by 2 values. So 0.01, to turn that into a percent, we're multiplying by 100 and adding a percent sign. All right, so what we end up with is 1%. This has been already rounded. There's no rounding to do in this problem, so it happened to be a whole percentage. So this worker, after he looks over his wages for this last 4 or 5 years, sees that his wage is only going up by 1% every year. Now, while that is exponential growth, it's going to take a long time for his wage to go up significantly. Part F of this problem is getting into a concept that is very relevant, across our history, but it's relevant especially to you today. We're talking about the idea that the prices of goods and services has gone up 26% from the year 2000 to the year 2010. Okay, so for 10 years, actually that'd be from 2000 to 2009. For 10 years, they measured the prices of goods and they said, okay, all of those goods, those prices are going up by 26% total over that decade. We need to see, are the workers' wages increasing at on pace with the inflation of 26%? So here's what we're going to do. I need to know, what is the wage in the year 2000? Well, we already figured that information out in an earlier part of the problem. Okay, but it's also very sneaky. Right in the formula, this value here, 15.05, that is W of 0, right? And I'm writing W of 2000 just to kind of keep in mind, you know what, let's do this right. W of 0 in the year 2000 was 15.05. This is the amount of money that he made in the year 2000. 10 years later, use the formula to calculate what his wage is. See if you get the same thing as me. So I'm doing 15.05 times 1.01 raised to the 10th power, and his wage is 16.62 if we round properly to the nearest penny. Our job is to determine how much did his wage increase over the decade. In order to figure that out, I'm going to do this at the bottom. What we're going to do is make a ratio of the amount that he made at the end of the decade divided by the amount that he made in the beginning of the decade. So that's going to be $16.62 divided by $15.05. And when I worked that out and rounded to a few decimal places, I wound up with 1.106, right? I want to round to 2 decimal places. I just think it's the easiest way to compare. So I'm looking at the 3rd decimal place. Since it's greater than 5, I'm rounding up my 2nd decimal place. So this is going to be approximately 1.11. If this is the amount, this is the ratio of W of 10 over W of 0. What that tells me is that I have increased by a factor of 1.11. This is an A value. So I want to turn this into a percentage. Remember that A's are 1 plus R. So 1.11 equals 1 plus R. Let's do this calculation here. Just like before, we're trying to get R by itself, minus 1. So on the right-hand side, I've got 1 minus 1 plus R. Well, that's just 0 plus R, or R. And on the left-hand side, I have 1.11 minus 1. That gives me 0.11. I need to turn this into a percent. They told us the inflation as a percent, so we need to be able to talk about our wage increase as a percent. The way we do that is we multiply by 100 and write the percent sign. Okay, so what we wind up with is 11% is equal to R. 11% is how much our wage went up over the decade. So if the prices of all of the things you have to purchase in order to survive go up by 26%, but your wages only went up by 11% that decade, your wage did not keep up with the inflation of the economy around you. All right, so you don't have the same buying power. You can't afford the same amount of goods in 2010 as you could in the year 2000. You are effectively poorer because your wage did not keep up with inflation. So to answer part F, at least with the numbers that I was given in this problem, the wage increases were lower than the inflation rate. And so this worker, again, would not be able to afford the same apartment, the same car payment, the same loaf of bread would be effectively more expensive for them in the year 2000 than it was back in the year 2000.